Okay, so today we're going to look at a new topic and we're going to be looking at what we call chi-squared distributions. So let me start by taking you through a scenario. If I had a coin, which I'm told is a fair coin, or I can assume is a fair coin, and I flicked it 60 times, I want to know the count of each outcome. So the number of times that each outcome happened. And I'm going to try and use that to determine whether the coin was fair or not. To do that, I'm going to compare the frequencies that I get with the expected frequencies. Flipping a coin 60 times, I would expect to get 30 heads and 30 tails. Now, we know there's some randomness attached to the outcomes we get when we're flipping a coin. So, a fair coin could still produce 29 heads and maybe 31 tails. It could be 28 and 32. 25 and 35. But at what point do we start to think this is no longer a fair coin? That's what we're going to look at today. A measurement which helps us to decide if it's too far away from the expected frequencies. So, we're going to look at a way to decide if there's evidence to support that it's a fair coin or a biased coin, and we're going to need a statistic, a measurement which helps us to determine whether or not it's just too far away from the expected values, from the expected frequencies. So, in the wonderful world of statistics, we actually have a measurement that helps us to do this. This is our chi-squared test statistic, and it's calculated as shown. So to read this is going to be the sum of each individual occurrence of an observed value minus an expected value, all squared, divided by the expected value. So we're basically finding the difference between what happened and what we expected to happen. We're squaring it to make sure we've got a positive value, and then we're dividing it by the expected. So we're kind of getting a proportion of difference for this squared value from the expected value. If the difference is small, it will be a small proportion, like 0.1 or 1/3 or something quite small. If the difference is actually quite large, we might get a value of 3 or 7 or 18, depending on the values we're working with. So we're going to sum all of these together. If they're substantial, if they're significant, if they're quite large, then we know that we can doubt the stated distribution. But if it's quite small, if it's a small value, that leads us to think actually it does fit in with the distribution we were talking about in the first place. Okay, so let's try that calculation in these two instances. So for each outcome, I'm going to look at the observed and the expected. Okay, so the observed is 29, subtract the expected of 30, that needs to be squared, and divide by 30. The second time round, it's 31 minus 30, all squared, divided by 30. Okay, because there's only two outcomes, both of them are going to have the same difference from their expected value. So I've got 1 squared over 30 plus 1 squared over 30, which gives me a chi-squared test statistic value of 0.0667. Okay, that seems quite small. What would we expect in this second instance? 23 minus 30 squared over 30 plus 37 minus 30 squared over 30. This gives me 7 squared over 30 twice, and that gives 1.6333. So, even just looking at these two chi-squared test statistic values, we can see that on the left-hand side, where the difference from the expected was quite low, we had a low chi-squared value. Each contributing chi-squared component was quite small. On the right hand side, where the difference from the expected value of 30 was larger, we had a larger chi-squared score. Each contributing factor, both of them or each of them were 49 over 30, which is bigger than 1. So we're starting to see that we can calculate a chi-squared score and at least make some comparisons between two different distributions or between two different observed data sets. Okay, so hopefully that was straightforward and quite simple actually, because each contributing factor for the chi-squared test statistic calculation was the same value. So let's try something with more than just two outcomes. So a similar situation where we flip a coin and we're trying to see whether or not we have some evidence to suggest that the coin is fair or not. So the expected frequencies if I flip a coin 120 times is that each outcome happens 20 times. I'm going to go ahead and calculate the chi-squared statistic for this. And just as before, it's the observed and the expecteds that correspond that we work with. So 23 minus 20 squared all over 20. 15 minus 20, numerator in brackets and squared, all over 20. 25 minus 20, I'm going to square that and all over 20. We can see the denominator is going to be 20 every single time. But we'll just carry on, making sure we write out each of these calculations so that we have every contributing value to the chi-squared test statistic. Okay, these differences I can actually do in my head quite quickly. So I know this is 3 squared, then we have 5 squared, another 5 squared, 2 squared, 1 squared, and finally 2 squared over 20, which gives us an answer of 3.4. So a chi-squared score of 3.4. An optimal score would be 0. If it fit the expected values exactly, it would be 0. But anything close to 0 is also understandably a good fit, because we know the randomness of an experiment, we're not always going to hit our expected exactly. But the further away from 0, the more suspicious we get that it doesn't fit the given or the stated distribution well. Okay, let's just look at another example where we're making a comparison between two. Billy and Mel each have two four-sided spinners numbered 1 to 4. Now they each carry out experiments where they're going to spin both of their spinners and they're going to add up the score together. So two spinners, 1 to 4, if we added the scores together, the minimum score would be 2, while the maximum score will be 8. So those are the range of outcomes that we might get. After each of them has done 160 experiments, they've compiled their table of frequencies, and that's demonstrated below. The expected for each of those we would be able to see from a sample space diagram is given as well, where a score of 2 and a score of 8 are the least likely to occur, where a score of 5 is the most likely to occur, and these have expected frequencies of 10, 20, 30, 40, 30, 20, 10. Alright, we've been asked to give the null and alternate hypotheses for each of their experiments, and we've then been told that one of the students has a biased spinner. Which of the two do we think is most likely to have the biased spinner? Okay, before we even get into this, remember that the optimal result from a chi-squared distribution is 0. So the smaller the number, the closer it is to 0, the more likely it is to fit the distribution that has been suggested. The larger the number, the less likely it is to fit the distribution. So basically, we're going to try and calculate the chi-squared test statistic for both Billy and Mel. Whoever has the smallest value is most likely to fit the distribution of the expected values, and whoever has the larger value is more likely to have the biased spinner, is more likely to have the spinner that does not fit the distribution of expected values. Okay, let me walk you through the calculation I will do here. First, I'm actually just going to separate out the data. So I'm only going to look at Billy's to begin with, and I'm going to set some hypotheses. The null hypotheses every single time with a chi-squared distribution test, or what we call a goodness of fit test, is to say that the observed values fit the expected values well. To say that the observed values are a good fit for the distribution that contains the expected values. In this case, if they fit well, it means it is a fair spinner. So my null hypothesis is that Billy's spinners are fair and they fit the theoretical distribution, since this distribution doesn't have a specific name. So it's just that they're fair and they fit the theoretical distribution. My alternate hypothesis is that Billy's spinners are not fair and they do not fit the theoretical distribution. Okay, so we just got to get those hypotheses, and that's the way around. The null is that it is a good fit. The alternate is that it is not a good fit. These need to be written in words. Very often, or up to now, your hypotheses have been about a population parameter, but now we need to write our hypothesis as a statement in words. Okay, so we're going to go ahead and apply our chi-squared test statistic as usual. The observed minus the expected, all squared over the expected. So that gives us 15 minus 20, square it, all over 20. 22 minus 30, we're going to square it, and we're going to write it over 30. 41, subtract 40, square that difference, over 40. 39 and 30, we're going to calculate its difference, square it, divide by 30. 21, subtract 20, brackets, square it, divide by 20, and finally it's 16, subtract 10, square that, and write it all over 10. Okay, so we're just going to quickly calculate those differences in our heads. Once again, this should be quite easy and straightforward. I've got 2 squared over 10, 5 squared over 20, 8 squared, 1 squared, 3 squared, 1 squared, and 6 squared. Okay, just be careful to make sure you write these out with the correct denominators and write it out in full. Go to your calculator, we're going to punch that in, and we get 7.7583. So that was the chi-squared test statistics score for Billy. We're now going to calculate a similar thing for Mel. If Mel's score is higher, we're going to assume she has the biased spinner. If Billy's score is higher, we're going to assume he's the one with the biased spinner. Okay. So just like before, 6 minus 10 all squared over 10. The difference between 12 and 20, we're going to square that and write it over 20. 21 minus 30, square it, and it's over 30. 37 and 40, that difference, we need to square it, and we're going to write it over 40. The gap between 35 and 30, we'll square that and write it over 30. 29, subtract 20, let's square that. What is that as a proportion of 20? And the gap between 20 and 10, we're going to square that and write that over 10. Okay, so that leads to the calculation that's going to go into the calculator. 4 squared over 10, 8 squared, 9 squared, 3 squared, 5 squared, 9 squared, and 10 squared. Okay, I'm going to pick up my calculator, punch these in, and we get a chi-squared test statistic value of 22.608. Now, Mel's chi-squared test statistic value is quite a lot higher than Billy's. So if we know that one of these two spinners is definitely biased, out of the two of them, I would confidently say that it was Mel's that was biased. So in this particular case, I would conclude that Mel is the one who's likely to have the biased spinner. So for today, I just want you to really get some practice on calculating this chi-squared test statistic value. Go away and get stuck into some practice questions, and in the next session we're going to look at how to do a full hypothesis test based on the chi-squared test statistic.